Hi everyone, this is Tushar from Rasainika, expert for chemical sciences. So today I'm back with another video to help you calculate magnetic moment for transition complexes and inner transition complexes, that is F block element. So be with me till the end and I'm sure you will understand this concept very easily. These are very important concepts in terms of CSIR net and gate because every year we get at least one question. Even for basic questions from BAC also we have concept from this. So moving to the magnetic moment is represented by mu. This is the symbol for magnetic moment. Now the unit for magnetic moment is Bohr magneton. It is important. The unit for magnetic moment is Bohr magneton. Now coming to inner transition complexes, for inner transition complexes, it is important to note that the spin orbital coupling is very less for it. Now, what is this? Let's understand. Now, we all know that the center of an atom is nucleus and it is positively charged, and around it we have electrons orbiting in various orbits. Let's say this is the electron. Now, an electron has two types of motion in each orbit. It will be revolving around the nucleus, that will be its orbital motion, and along with that this electron will be spinning around its own axis. So for orbiting around the nucleus, the electron will have angular orbital momentum, and for revolving around its own axis it will have spin angular momentum. So here we have two things. We have S, which is spin angular momentum, and we have L, which is orbital angular momentum. Now these two parameters influences the magnitude of mu. Okay, so as I have said earlier, for transition complexes the spin orbital coupling, this coupling between L and S is very less. So for complexes where even though it is less, but we can observe both spin orbital momentum. So in complexes, even though in transition complexes the spin orbital coupling is very less, but for complexes where we can see both the spin momentum and the orbital momentum, we can use this formula which is given by mu equal to 4s into s plus 1 plus L into L plus 1, where s is the, as I have stated earlier, it's the spin angular momentum and L is the orbital angular momentum. So the important thing to note here is this is when we are observing both, when we are observing spin and orbital. In first row transition elements, generally from scandium to zinc, we observe a thing. What is that? We observe that in these complexes, particularly in first row transition complexes, we see that the orbital angular momentum, which is L, which is represented by L, is quenched. Why it is quenched? Due to the interaction of the ligands. Due to the interaction of the ligand electric field, the orbital angular momentum is quenched, so it will be zero. In that case, for the first row transition complexes, we can use this formula where the magnetic moment is given by root over of 4s into s plus 1, where s stands for the spin angular momentum. Now what do we know? This is the spin angular momentum. Now in terms of n, which is number of unpaired electrons, we can write the spin angular momentum is n by 2. Okay, because n is the number of unpaired electron. Let's say we have one unpaired electron, so s value will be half. Let's say we have two unpaired electrons, so accordingly s value will be 2. Okay, so for s we know s equal to n by 2. Okay, now we can just simplify this equation, which is given by mu equal to 4s into s plus 1, where we can just substitute s equal to n by 2 to get the very formula which we are very familiar, which is mu equal to n into n plus 2's root over, where n is nothing but the number of unpaired electrons in the complex. Okay, so I'll just write this. This equation can be modified where mu is equal to n into n plus 2 root over. I'll write in the upper part, mu equal to n into n plus 2's root over, where n is the number of unpaired electrons. So this is all about transition complexes. So you should understand which formula to use where. So you can use this formula when you have complexes where there is only spin momentum. Okay, and this formula you can use in complexes which has both spin and orbital contribution. So I hope this part is clear. Now moving to the inner transition complexes. Now for inner transition complexes, they have large spin orbital coupling. Okay, and the important thing is the orbital contribution is not zero. The orbital contribution, orbital angular momentum is not quenched. Now why? Because for inner transition complexes, generally the configuration is 4f. The configuration is 4f, and we know that these 4f orbitals are shielded by 5s and 5p. So they are shielding this, they are protecting this orbital from outer experiences of the ligands. So they are not affected. These 4f orbitals are not affected by the ligand surrounding it. So that is the reason why here the orbital momentum is not quenched. Now in these complexes, we have, since we have two parameters, new parameters, since we have a larger spin orbital coupling and the orbital motion is not quenched, so here we need to use the formula mu is equal to g, where g is given by this. I'll just explain in a bit. And what is g? G is Landis splitting parameter. It's Landis splitting parameter or factor, we can say. Okay. Now what is j? Now what is j? J is the coupling constant. J is the coupling constant we get after the coupling of L and S. Now it is important to note here one thing. Now depending upon the orbital, depending upon the number of electrons in the orbital, this J value changes. I'll write it over here. J is equal to L minus S when it is less than half filled. When it is less than half filled. And when the number of electrons are greater or it is more than half filled, then we have L plus S when it is greater than half filled. So these two things you need to keep in mind when finding the value of J. So J is L minus S when it is less than half filled, and J is L plus S when it is more than half filled. Okay, so this is all about J, and we can calculate the value of G using this formula where G is given by 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1, where, as I have already stated, S is the spin angular momentum and L is the orbital angular momentum. Okay, now let's do an example and understand it in a better way. Now coming to two examples, let's start with the cerium 3 plus. This is the most common example that we can, and easy example that we can take to understand this concept. Let's start with cerium. So what is the configuration for cerium? The configuration for cerium is xenon 4f1 5d1 6s2. It is important that you remember these configurations for lanthanides and actinides, because in exam you will be having simple questions from magnetic moment, but it is important that you remember this electronic configurations, otherwise you won't be able to solve it. Okay, so cerium is given by this. So cerium 3 plus. So cerium 3 plus, what is 3 plus? 3 electrons will be lost. So from where it will be lost? It will be lost from S6s2, 2 electrons will be there, those 2 will be left, and 1 from D. So what we are left for cerium 3 plus, the configuration will be xenon 4f1. So we have only 1 electron in the f orbital. Now what do we know? We know f orbitals have 7 in number. 1 2 3 4 5 6. So this is plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3. We know for f orbital 7, there are 7, and for them the value L values changes from L equal to plus or minus 3. That is why we are having from plus 3 plus 2 to minus 2 minus 3, this range. So we have 1 electron here. So where can we fill? We can just put 1 electron over here. So now the next task for you is to calculate the value of L and S. Now as you can see, the L value for this is plus 3. L is plus 3. Now what is S? Now it is the value for the s. Since there is only one single electron, so the value for s will be half. And already have said how to find j. Since it is less than half filled, the j value will be L minus s. Okay, since it is less than half filled, the j value will be L minus s. So just you can put, so j is equal to 3 minus 1 by 2, that is 5 by 2. Okay, from this we have got the value of s, the value of L, the value of s, and we have got the value of j. So just I'll write it down here. So what we have got for cerium 3 plus, we have got the value for j is 5 by 2, the value for s is 1 by 2, and the value for L is 3. Now the next task is just to compute the form using magnetic moment using the formula. So it will be G into J plus 1. We have J here. What is the next thing that we want to find? We want to find the G. So what is G? G equal to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So then it's very simple. Just put in the values for S. We have S here, L here, and you compute it. So after computing these values, you will get 3 by 2 plus, just put on the values and solve for G. I'll just remove this so that we can have a greater thing. So mu is G into J plus 1. So you compute the G, keeping all the values. So we can solve this. After solving this, you will get 6 by 7 into root over of 35 by 4. Now once you solve it, approximately you will get it to be 2.54 Bohr magneton. So the main task here was to calculate the value of J. I showed you how to calculate it. And L and S. Once you get those values, just plug in and solve it. You will get it 2.54 Bohr magneton. Now coming to the next question, I'll just give you a few hints and you can solve it by yourself. For erbium, the configuration is 4f12, 5d0 and 6s0. Okay, so now when it is losing electrons, now coming to the next example, erbium. So the electronic configuration for erbium is, xenon is of course there. It is 4f12, 5d0, 6s2. This is the electronic configuration for this. Xenon, 4f12, 5d0 and 6s2. Now for erbium 3 plus, the 3 electrons will be lost. So what we will have? We will have 2 from here and 1 from f orbital. So we will be having 4f11. Okay. Now we need to arrange this 11 electrons and calculate the value for S and L. So we have f11 in 4f orbital. Now we need to arrange them. Let's just draw 1, 2, 3, 4, 5, 6 plus 3 plus 2 plus 1, 0, minus 1, minus 2, minus 3. Just simply draw the f orbitals, write the L values starting from plus 3 from left side to right side till minus 3 and just draw the electrons in them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now after that you can calculate the value of L, the orbital angular momentum, the summation of these small L values. Now just check it. What is the resultant after this calculation? So all this will be cancelled. We will be left with 3, 2, 5, 1, 6. So it will be 6 for us. Okay, just check it. This will be getting cancelled. Plus 3, plus 2, plus 1 will be left eventually. You just need to add this and find the resultant. And for same for S. So how many pairs we have? 1, 2, 3, 4. So only 3 unpaired electrons are there. So it is 3 by 2. So you have the L value. So you have the L value of 6 and you have the S value of 3 by 2. Okay. Now what is the next text? You need to find J. Now, how will you find J? Check what is the configuration. Is it greater than half filled? Yes, it is greater than half filled, because for half filled f orbital it is f7, it is 11, so it is more than half filled. So you will use the formula L plus S. Okay, now 6 plus 3 by 2, 15 by 2. It's coming 15 by 2. So you have your 15 by 2. Now you just need to calculate G. 3 by 2. I'll just write here. So S is this. I'll just erase this part and write it over here. So G is equal to 3 by 2 plus, what is S? 3 by 2 into S plus 1. Just remember the older formula. Plus, sorry, it's minus. It's minus L. What is the L value? 6 into 6 plus 1 divided by 2J. 2 into 15 by 2 into 15 by 2 plus 1. Once you solve this, you will be getting the G value, and once you are done with the G value, you can just substitute this G into this formula and get the answer. So the important task here was to find the value of J, L and S. I am sure you got the answer, and I want you all to try this question and solve it by yourself. I am sure after this session you will be having a clear-cut idea how to find the magnetic moment of transition metal complexes and inner transition metal complexes. Thank you all for being with me. Please like, subscribe to our channel Rasainika. We will be getting more such content on this. Thank you.